Japan's maglev trains, a pioneer in modern transportation, do not require physical contact with the rails. This allows for smooth operation in all weather conditions and significantly reduces maintenance costs thanks to low friction and few moving parts. However, despite its many advantages, there is only one commercial high-speed maglev line currently in operation, and it is only 30 kilometers long. The line completes the journey in 8 minutes, but such a short distance reduces the efficiency of high-speed maglev trains. With an average speed of only 225 kilometers per hour, maglev trains are even slower than conventional bullet trains. Meanwhile, the future high-speed maglev network is expected to be only 400 kilometers long, compared to the massive network of 60,000 kilometers of existing conventional bullet train track and 50,000 kilometers under construction. Why is there such a big difference? Let's explore how maglev trains work and explore the reasons behind the limited implementation of this groundbreaking technology. There are two main methods of levitating maglev trains: levitation and propulsion. The first method is levitation. In this system, magnetic iron rails and electromagnets are used to create suction, lifting the train body off the track. This is an active system, meaning that the distance between the rails and the magnets needs to be constantly adjusted to maintain an effective suction. This distance is important because the strength of the suction decreases sharply as the distance increases. If the train starts to fall, the suction will quickly weaken, causing the train to fall even further. For this reason, the system is unstable and requires active controls and feedback loops to ensure that the distance is always between 8 and 12 millimeter. This is the type of system that the 30 kilometers long maglev line in Shanghai uses. Japan has chosen a different method with a larger distance between the rails and the train, about 10 centimeters, 8 times that of the electromagnetic suspension system. This provides a stable passive hovering method, which is very important in an earthquake-prone area like Japan. In this method, the magnets on the train interact with passive coils on the rails. As the train moves over these coils, the changing magnetic field will create an opposing magnetic field, lifting the train. However, this system only works when the train has reached a certain speed, because when the train is stationary, the magnetic field does not change, and the train will not be able to fly. Japan's propulsion method not only makes the hovering train more stable, but also better suits the country's geographical conditions, bringing greater safety and efficiency in operation. As the maglev train slows down, the wheels will lower, and when it reaches a speed of 100 kilometers per hour, the wheels will fold inwards. To maintain a stable position on the track, the north and south poles of the magnets are arranged vertically on either side of the track. The magnets on the train are made up of coils arranged in a figure-8 shape. If the train drops or veers to one side, the magnets will induce a current in the opposite coils, creating a stronger magnetic field to push the train back to the center position. This system maintains a distance of 10 centimeters between the train and the track without the need for complex controls. Japan's maglev train, called L0 or S maglev, uses superconducting coils to create a strong magnetic field. These niobium titanium coils are cooled by liquid helium and placed in a tank cooled by liquid nitrogen. The cooling process uses sound waves, similar to the James Webb Telescope, to maintain extremely low temperatures and ensure that the current flows without resistance. Sound waves create a compressed area with high pressure and temperature in a closed tube, which helps maintain the necessary temperature for the superconducting coils. This allows the maglev train to operate stably and efficiently. To cool the superconducting coils of the maglev train, a chimney is used to extend from the hot zone at the end of the tube to the cold zone in the middle. Heat exchangers placed at both ends of the chimney transfer heat, keeping the coils cold. Each train car has 8 such coils, 4 on each side. Since strong magnetic fields can be dangerous to passengers, engineers need to ensure that the magnetic field does not spread into the passenger compartment. They cannot block the magnetic field, but they can redirect it using electrical steel. Electrical steel contains 3% silicon and is processed to create large crystal grains in a specific direction, which helps direct the magnetic field more effectively. To reduce the mass of the shield, the engineers also manipulated the shape of the magnetic field by arranging the magnets in parallel. By flipping the magnets so that their north and south poles faced each other, they created a weak magnetic field between the coils on either side of the cabin. Using both the steel shield and this magnet arrangement, the magnetic field strength in the passenger compartment was reduced to 0.5 meters per, which is comparable to the Earth's magnetic field. However, near the magnets, the magnetic field strength is still high, requiring the use of low magnetic materials or fiber-reinforced composites for the rails. These measures ensure passenger safety and optimal performance for maglev trains. How can a maglev train propel itself if it does not touch the ground? Instead of using wheels and torque like a conventional train, a maglev train uses a linear motor system. This motor works by replacing the coils from a conventional electric motor to create a continuous pull and push, helping to push the train forward at precise timing. When braking is required, this system can work in reverse, called regenerative braking, which helps to reuse energy. At low speeds, maglev trains have additional wheel brakes and air brakes to slow down. But how does the train receive electricity when it does not contact the rails? At low speeds, the train uses a third rail with low friction, as in a subway system. However, at high speeds, this is no longer practical because it loses the friction-reducing advantage of maglev trains. Japan's solution is to use a linear induction coil to harvest energy from the changing magnetic field of the guide coils. This creates a magnetic resistance, but is more efficient than carrying a large generator on the train. Japan is expected to open its first high-speed maglev line, a 285 kilometers line between Tokyo and Nagoya, in 2027. Japan has long been a pioneer in train technology, and they are continuing to lead with maglev trains. After the success of the Shinkansen line from Tokyo to Osaka in 1964, Japan began researching ways to shorten the journey from 4 hours to under 1 hour. Since the 1970s, Japan has built a 7-kilometer test track in Miyazaki. Starting with prototype trains that could reach speeds of 60 kilometers per hour in 1972, by 1995, they had developed trains capable of reaching speeds of up to 411 kilometers per hour. When the Miyazaki test track proved too short, the 20 kilometers Yamanashi test track was built in 1990 between Tokyo and Nagoya. In Yamanashi, Japan has developed a full-scale train capable of carrying 700 passengers in 12 carriages at speeds of 500 kilometers per hour. The maglev train is not only a science experiment, but also a super-fast and efficient way to move people. The first phase of the maglev line from Tokyo to Nagoya, which will be 285 kilometers long, is scheduled to open in 2027. The second phase, which will run 438 kilometers to Osaka, will be completed a decade later. Building a maglev train is not only a technical challenge, but also an economic one, competing with cars, planes, and other types of trains. When discussing maglev trains in the United States, the idea of traveling between New York and Los Angeles in 7 hours is often mentioned. However, such a long distance does not make much economic sense. When considering the travel time between San Francisco and Los Angeles, the train is still the best option. Currently, maglev technology is mainly used for special projects due to its high construction costs. For example, building a maglev line from Tokyo to Osaka is a huge investment, and there is no clear sign of the technology expanding beyond mainstream projects. In the United States, the development of modern rail service is struggling. Major cities such as those in the Texas Triangle still rely heavily on the interstate highway system, despite the great potential for rail. Advances in room temperature superconductivity technology could make building maglev trains easier and more cost-effective. This is attracting a lot of interest, but you don't need a comprehensive college course to understand the basics of how magnetic fields work and the technologies involved. Maglev technology, while not yet widely available, is still an important step forward in the transportation industry and could change the way we travel in the future.